Lesson 1, Momentum and Impulse. We'll start with a review of scalars, vectors, and units. Just a basic overview. We'll get a little bit more deep into vectors and units later in the course. Scalars are measurements that have magnitude only. Magnitude is the word we use in physics for amount, or the number part of a measurement. Vectors are measurements that have magnitude and direction. This means they have an amount, but they also have a part of it that tells you which way that magnitude points. Examples of scalars include speed, time, mass, distance, and energy. The math that we do with scalars is much simpler. You can just add scalars together without worrying about addition or subtraction or direction, because scalars have no direction. Vectors, on the other hand, have more complicated arithmetic associated with them because of the direction part. These are quantities like velocity, acceleration, force, and the topic for today's lesson, momentum. When you're using velocity, acceleration, force, and momentum, it's not just enough to know how much their magnitude is, you also need to know which way they're pointing so you can really understand how they're interacting with the objects associated with them. Vector notation. Notation is a series of rules used in math and science for how things should be written. In vector notation, you should always draw an arrow over the vector symbol. So for example, if you're using velocity to distinguish it from speed, we draw a little arrow over top to show that it's a vector. We also put the direction in square brackets next to the unit. So for example, if you have a velocity of 10 meters per second, you put the direction in square brackets next to the unit. Using vectors in calculations. Again, we're just going to go over a basic overview, later looking more deeply at vector addition. You should know that there are positive directions. Positive directions are all given a positive sign when used in calculations. These are north, east, forward, up, and right. If we're looking at our xy coordinate system, positive directions are the directions that form the positive y-axis and the positive x-axis. Negative directions are south, west, backwards, down, and left. These are the directions on our xy coordinate system that are associated with the negative x-axis and the negative y-axis. Now, the plus or minus sign is considered to be a direction indicator. Don't write the negative and the direction. You would write velocity equals 10 meters per second west, or velocity equals 10 meters per second negative. Don't write the negative and the west. Negative west means east. The plus or minus sign is considered to be a direction indicator itself, so you don't actually have to write the direction. The negative is the direction. If you write negative and a direction, you end up flipping your direction, and your answer doesn't mean what you think it means. Units. In the SI unit system, which is the unit system we use in science, there are 7 base units. In Physics 20, you only learned about 3, meters, seconds, and kilograms. But in total in the SI unit system, there are actually 7. The meter, the second, and the kilogram are the ones that were going to matter to you the most now. Now be careful. In physics we use the kilogram, whereas in chemistry they tend to use the gram more often. Don't mix up physics and chemistry. The other units are called derived units, and they're constructed from these base units. For example, acceleration has the unit meters per second squared. This comes from the formula for acceleration, where acceleration equals velocity over time. So that's meters per second divided by a second gives you a meter per second squared. For force, the unit for the force is generally called the Newton, but it can be constructed from the meter, the second, and the kilogram. For example, formula for force is F equals ma, which is a kilogram times the meter per second squared for the acceleration. So we know that 1 Newton of force is the kilogram meter per second squared. The Newton itself is a derived unit. It's not a base unit. It's made of the kilogram, the meter, and the second. Energy also has a derived unit. For example, one formula for energy that we use is potential energy equals mgh. The unit for mass is kilogram. G is a type of acceleration, so it has a meter per second squared, and height is a meter. A kilogram times a meter divided by second squared times another meter gives you a kilogram meter squared per second squared. Now that's a little bit too much to write every time you write out a measurement for energy. So they give that a single symbol called the joule. So 1 joule is a kilogram meter squared per second squared. Finally, we have energy. Energy is another concept, or power is another concept associated with energy. The typical symbol for power is the watt. Power is energy over time. We've already seen that energy is measured in joules, so that's joules per second, or a joule is a kilogram meter squared per second squared. That divided by a second is a watt. So a watt is a kilogram meter squared per second cubed. There are some basic unit conversions you should be able to do. You should already be able to convert metric units from one prefix to another, but here are some of the most common ones. You need to be able to convert a kilo to the base unit, whether it's a kilogram or a kilometer. The conversion factor for kilo is 1,000. Kilo means 1,000. So a kilometer times 1,000 will give you a meter, and a meter divided by 1,000 will give you a kilometer. The same goes for kilograms and grams. You need to be able to convert kilometers per hour, which is the most common unit of speed used in everyday life, into a meter per second, which is the unit used in physics for speed and velocity. The conversion factor is 3.6. A kilometer per hour divided by 3.6 gives you meters per second. Meters per second times 3.6 gives you a kilometer per hour. One of the ways I remember this is I noticed that a kilometer per hour has 3 letters, a K, an M, and an H, and the division sign has 3 parts. So if I want to divide a kilometer per hour, if I want to convert a kilometer per hour into meters per second, I know to divide because it has 3 letters. Meters per second has 2 letters, and the time sign has 2 parts. So I know that if I want to convert meters per second to kilometers per hour, then I would multiply because of that. Finally, you need to be able to convert from hours, which is the unit we use in everyday life for time, to seconds, which is the unit used in physics. The conversion factor for this is 1,000 times 3.6 is 3600, or 60 times 60, because there's 60 seconds in a minute and 60 minutes in an hour. An hour times 3600 will give you a second. A second divided by 3.3600 will give you an hour. Next, we're going to look at 2 fundamental concepts for this unit, momentum and impulse. Momentum is defined as the product of an object's mass and velocity. mass given in kilograms with the symbol m, and velocity given in meters per second with the symbol v. Don't confuse the m as in mass with the m as in meters. One is a symbol, the other is a unit. Momentum is given by the symbol p, with an arrow over top of it to say that it's a vector. I don't know why they chose to use the letter p. It's got not much to do with momentum. It might be because they'd ran out of letters of the alphabet. M was taken by mass and meters, so it couldn't be used again. So they chose p. The unit for momentum is the kilogram meters per second. There isn't a special symbol for this derived unit. It's just the collection of kilogram meters per second that forms momentum. The formula for momentum is P equals m times v, where P is momentum measured in kilogram meters per second, m is mass measured in kilograms, and v is velocity measured in meters per second. The direction of the velocity will be the direction of the momentum. An object can have a large momentum either by having a very large mass and a slow velocity, or a tiny mass and a very fast velocity. For example, an elephant is a fairly slow-moving creature. An elephant has a very large momentum because it has a very large mass. On the other hand, a bullet could have a similarly large momentum, but it's a very small object. A bullet, because it moves very fast, also has a high momentum. When you think about momentum, I want you to think about how much it would hurt if that object were to collide with you at that speed. An elephant, moving very slow, would still probably hurt quite a bit if it ran into you. A bullet, though small, is moving so fast that it also hurts when it runs into you. Momentum is all about how much force an object is capable of transferring. Here's an example for the elephant. An elephant with a mass of 1,800 kilograms walks at 0.21 meters per second. What is the elephant's momentum? Momentum equals mass times velocity. So the momentum is the mass of the elephant times the elephant's velocity, giving us a momentum for the elephant equal to 3.8 times 10 to the 2 kilogram meters per second. And again, the direction for the momentum is the same as the direction for the velocity. So in this case, it's east. Here's a second example. What is the momentum of a 0.050 kilogram bullet moving at 2,000 meters per second to the left? The momentum of the bullet will be given by m times v. So this is the mass of the bullet times its speed, or velocity. So the momentum of the bullet is equal to 1.0 times 10 to the 2 kilogram meters per second. And again, the direction is the same as the velocity, so that will be to the left. You can see these two objects, even though they're quite different in size, have similar momentum, because the elephant is going slowly and the bullet's going quite fast. Impulse is the second concept associated with momentum. Momentum is most useful in physics problems involving collisions and explosions. Remember, momentum is most useful when you think about how much force the object could transfer if it was traveling at that speed. Transfer of force usually occurs during a collision or an explosion. A collision is a short interaction between two objects. During a collision, an impulse is transferred from one object to another. This is the same as saying a force is transferred from one object to another, but it's a more precise definition. Impulse has the formula impulse equals force times change in time. Impulse has no symbol. We just write out the word impulse. The unit for impulse comes from the formula. Force times time gives you newtons times seconds. force is in newtons, and time is in seconds. Now, delta notation is something you should be familiar with from Physics 20. Delta means change in. Delta, or triangle, is a Greek letter, and it's used to symbolize a quantity that has changed. So the impulse is the force times the change in time, or the time interval that the force took place over. Here's an example. During a collision between a tennis ball and a racket, an impulse of 0.425 newton seconds is transferred to a ball in a time interval of 0.025 seconds. What was the force on the ball? Impulse is equal to the force transferred times the time interval it was transferred in. We can rearrange this to give us force equals impulse divided by the time interval, which is 0.425 divided by the time interval of 0.025 seconds. This gives us a force imparted of 17 newtons. We can connect the concepts of impulse and momentum. Now, I've already explained to you that momentum is most useful in an event where you have a collision or an explosion. Impulse is the force transferred in that time interval that there is a collision or an explosion. Now, we can connect these two formulas by looking back at some of the formulas we knew before. Recall Newton's second law, which is F equals ma. Now, impulse equals F times delta t, and force equals mass times acceleration. So we can rewrite this to give us impulse equals ma delta t. Also remember, back from Physics 20, that acceleration is change in velocity over change in time. This gives us impulse equals m delta v over delta t times delta t, and whenever you have the same quantity on the top and bottom of a fraction, it can be cancelled out. So this gives us impulse equals m delta v. Now, m delta v looks very familiar. Momentum is mv, so it makes sense that m times change in velocity would be a change in momentum, or delta p equals m delta v. What this tells us is a really important thing about physics. Impulse is equal to the change in momentum. The way we would write this out is F delta t equals m delta v. Impulse, F delta t, change in momentum, m delta v. Now, if you examine your formula sheet for momentum and energy, you'll see some familiar formulas that we've gone through in this video so far. Momentum formula, P equals mv, is there, but you won't see the impulse formula. That's because the impulse equals change in momentum formula is listed, and they don't want to list it twice. So F delta t, impulse, is given there, m delta v, change in momentum, is also listed, but they don't list them individually. It also is useful because it shows this relationship, F delta t equals m delta v, or impulse equals change in momentum. Analysis. Now, I showed you for impulse is F delta t, which has the units Newton seconds. Change in momentum is m delta v, and we use the momentum units kilogram meter per second. I'm going to show you that the Newton second and the kilogram meter per second are interchangeable. Even though when you're using impulse, you use the Newton second, and when you're talking about momentum, you use the kilogram meter per second, they actually are the same unit. So we know, because the Newton is a derived unit, that the Newton is the kilogram meter per second squared. Now, the kilogram meter per second squared times a second means that we end up canceling out one of the seconds. This gives us a kilogram meter per second. So, in other words, we can also show using unit analysis that impulse is equal to momentum. Here's an example. A racket hits a 0.057 kilogram tennis ball. For the 0.034 seconds that the collision occurs, a force of 47 newtons is exerted. What is the change in speed of the ball? We use this impulse-momentum relationship that we derived, F delta t equals m delta v, to calculate the change in velocity. Change in velocity would be F delta t divided by m, which is 57 times the change in time divided by the mass, which gives us 34 meters per second. Another good useful example of this F delta t equals m delta v relationship is airbags. Airbags lengthen the amount of time a victim's head takes to stop during the collision. So delta t becomes bigger, or a longer number. Now, we know that the change in velocity can't change. During a collision, you go from the same initial speed to the same final speed. The airbag isn't going to change the speed you were originally going at, and is not going to change the fact that you stop. Also know that mass can't change due to the airbag. The airbag isn't going to change the mass of your head at all. There's nothing that can be done, it's your head. So the only thing that can change is the force. In order for F delta t to be m delta v, where the m delta v can't change, stays the same, delta t becomes bigger. In order for the relationship F times delta t to still equal m delta v, the force has to become smaller. So the purpose of an airbag is to increase the amount of time your head has to stop in so that the force on your head becomes smaller. Final example, and this one's going to be a little bit longer. A 5 kilogram puck slides to the right at 10 meters per second on a frictionless surface, and it collides with a stationary 8 kilogram puck. The 5 kilogram puck rebounds at 2.5 meters per second to the left. What is the final velocity of the 8 kilogram puck? So it helps sometimes to draw a picture of the situation so we can properly visualize what's happening. In this situation, we have a collision, and we have a before the collision and after the collision. So before the collision, we have a 5 kilogram puck sliding to the right at 10 meters per second, colliding with a stationary 8 kilogram puck. Now, we then have a collision, and after the collision, the motion changes. The 5 kilogram puck is now going 2.5 meters per second to the left, and the 8 kilogram puck is probably also moving, and we want to find out how. Now, to solve this problem, it's best to realize that in the moment of the collision, Newton's third law still applies. Newton's third law is during an interaction, an equal and opposite amount of force is exchanged between the two objects. So the 5 kilogram puck experiences the exact same amount of force during the collision as the 8 kilogram puck. Since impulse equals F delta t is the change in momentum, and F is equal and opposite. So the force is equal and opposite during the collision for the two pucks. Therefore, the change in momentum for the two pucks must also be equal and opposite. Same amount, different direction. So, the momentum of the 5 kilogram puck before is equal to mv before, which is 5 times 10 is 50 kilogram meters per second to the right. And the momentum of the 5 kilogram puck after is mv, which is 5 times 2.5 to the left, is 12.5 kilogram meters per second to the left. The change in momentum for the 5 kilogram puck would be the momentum of the 5 kilogram puck after minus the momentum of the 5 kilogram puck before, which is 12.5 negative because it's left, minus 50 positive because it's right, is 62.5 kilogram meters per second negative, which means left. Now we know that the change in momentum of the 8 kilogram puck must be equal in amount and opposite in direction. This means that the 8 kilogram puck must experience a change in momentum of 62.5 kilogram meters per second to the right. Since the change in momentum of the 8 kilogram puck is equal to the momentum of the 8 kilogram puck after minus the momentum of the 8 kilogram puck before, and before the 8 kilogram puck wasn't moving, so 62.5 kilogram meters per second to the right is equal to the momentum of the 8 kilogram puck after minus 0, or just the momentum of the 8 kilogram puck after is equal to 62.5 kilogram meters per second to the right. This allows us to calculate the velocity of the 8 kilogram puck after the collision. Since P equals mv, v equals P over m, is 62.5 divided by 8 kilograms, which gives us 7.8 meters per second to the right.